Hello everyone, welcome to this video. In this video, we'll be discussing about fundamental theorem of group homomorphisms. So, unlike factor groups, we have learned about homomorphisms, right? So, factor groups, they cause a systematic collapse of group into simpler groups. This thing right? Similarly, the same thing also is present for homomorphisms. How? The features of the bigger group, they are present in the smaller group. So you have some bigger group, you have some Cayley table for it. This Cayley table can be reduced to a much smaller Cayley table here by the help of homomorphism, where all the properties of this Cayley table and this group is preserved here within this group and its Cayley table. However, the size is now reduced to a significant amount, right? So this thing could be related very well with that of this factor groups, right? You have already studied about that for a group G, for which we have some normal subgroup H. Its Cayley table can be arranged into boxes, right, which represent the cosets of H in G. This is a result that we have already showed, right? In fact, as I've told you, these boxes are nothing but the Cayley table for this factor group G by H, right? Similarly, in a homomorphism, if we relate it to this thing, for this H is what? It is the kernel of the given homomorphism phi, right? And it plays the role of a normal subgroup H. Right. So once we know this thing and see a relationship between cosets, factor groups and homomorphism, we can now obtain a relation for the same, which states that if you are given phi as some group homomorphism from some group G to G bar, right, then we have another mapping, let's call that mapping by the name psi, such that it takes this factor group which is generated by this normal subgroup kernel phi of G. You already know kernel phi is a normal subgroup of G, right? We have proved in the previous properties. So this takes to phi of G. This is a mapping, right? This mapping is defined like this: phi of G kernel phi. So that means a cofactor here constructed from the normal subgroup kernel phi would be phi of G, and this phi of G is the homomorphic image of G under phi, correct? So here we have to prove that this mapping psi is a homomorphism, and in fact these two groups, the factor groups generated by kernel phi and its homomorphic image of G under phi, they are isomorphic to each other. Now this is a very good result, right? We have various applications based on these groups. So let's see what are these applications. If we are given psi, as I've told you, as the given mapping which is defined in this manner, then we have to prove that it is an isomorphism. So, for an isomorphism, the mapping should be well defined. The mapping should be 1 to, it should be 1, 1, it should be on to, and it should be operation preserving, correct? So, in order to prove all of them, let's proceed by one. For well defined, what you do, you take the two elements as equal to each other, right? And we have to prove that their images are also the same. That means phi of G kernel phi is also equal to the psi of H kernel phi. Or what is this psi of G kernel phi? It is what? It is phi of G is equal to phi of H. You need to prove this thing for well defined. And for on to, we start with this thing and we wanted to prove this thing. We go in the reverse direction for 1, not on to. Okay. So for well defined and 1-to-1, we have a result which proves both of the conditions. We have already studied that if phi is given to be a homomorphism, then phi of A is equal to phi of B. This would be there if and only if A kernel phi is equal to B kernel phi, right? So we have a result. And what is this? This is your, actually by the definition, psi of A kernel phi, that is equal to psi of B kernel phi. So if you are given psi of A kernel phi equal to psi of B kernel phi, this is true when this is there, and this condition is there when we have this condition here. So we have both these properties well defined and 1-to-1 as valid here by this property, correct? Now let's move on to our next thing, which is on to. So clearly this mapping is onto Y because we have defined it in such a way that for every phi of G in phi capital G, right, we have a coset which is G kernel phi present in this factor group such that we have this definition, right? So for every phi of G here, we definitely would find some G. Why? Because phi is a mapping which takes G to phi of G, correct? So it is obviously onto because for every phi of G we have a G here, right? If we have a G, then corresponding to that we can clearly construct a coset out of it, which is G kernel phi, hence it is onto. Now next, in order to show that this psi is operation preserving, we have to prove that psi of two elements is equal to psi of the first element into the psi of the second element, right? So by the properties of coset, you can write x kernel phi, y kernel phi as xy kernel phi, correct? So now this becomes the definition. By the definition of psi, you can write it like this: phi of xy. Now because phi is a homomorphism, so therefore we have operation preserving property present within it, so it could be written like this: phi of x and phi of y, correct? And what is phi of x? It is psi of x kernel phi, and phi of y is what? It is psi of y kernel phi. And this is what we wanted to prove here. Hence all the four conditions are satisfied. Hence we have this mapping psi as an isomorphism between these two groups, G oblique kernel phi, which is the factor group, and this phi of G, which is the homomorphic image of G under phi, correct? So both of them, they are isomorphic to each other, and this is what we wanted to prove here in this particular video. So I hope you understood this video well. Well, that is it for this video. Thank you for watching.